thank the organizers for inviting me to this wonderful meeting. And as Vivek said, I'm going to switch gears and talk about the primate visual system. So the question of how the primate visual system achieves invariant object recognition is a question that has grabbed the attention of theorists and physiologists and experimentalists in general for several decades. So when you look at an image like this one, there are a lot of invariances that you can see. So we can recognize these electricals regardless of whether they're close to us, and so they subtend a large visual angle, or they're far away and appear smaller. We recognize these trees regardless of whether you're looking straight at it or it's off in the visual periphery. We recognize these hills regardless of whether they're partially occluded by pixels. And in the primate brain, such recognition is based on processing along the ventral visual pathway. So here I'm showing you the lateral view of the macaque brain, which is the animal model that we use in my lab. And the ventral visual pathway here runs from area V1 in the back of the brain to V2, V4, and the subregions of the inferior temporal cortex. In the first stage of this pathway, in area V1, neurons receive input from a small group of retinal ganglion cells. So they're basically getting input from a small region in the visual space. Okay, and via the LGN. So the first stop is LGN, and the first stop in cortex is area V1. As you go higher up in this pathway, the receptive fields get larger, and even at the level of IT, you're not getting input from the entire visual field. So you have this concept of a receptive field, which is the region in space where a stimulus would modulate the response of that. So in this sense, these neurons are all trivially not invariant. They're very position dependent. So when you talk about invariances here in these representations, we need to talk about invariance within the receptive field of the cell, and that's what I'm doing. At the level of V1, neurons can be broadly categorized into two categories: the simple cells and complex cells. Both groups of neurons can be orientation tuned and tuned to spatial frequency. But one big difference between these two is that with simple cells, you can divide the subregions into on and off subregions. You can divide the receptive fields into on and off subregions, where the ons are where luminance increments drive the responses of the neuron, and off subregions are where luminance decrements drive the responses of the neuron. Whereas in complex cells, you can't really parse the receptive field in this fashion. Okay, so what this means then is that if you take a sinusoidal grading of the appropriate orientation and spatial frequency that matches the subregions here, and you drift it across the receptive field of the cell, what you get is a modulation in the response. So when the increments match up and the decrements match up, you have a strong response. When they don't match up, you don't have a strong response. Okay, so in this sense, the simple cell is very phase dependent with the sinusoidal grading, and it is position dependent, so not position invariant. The complex cell, on the other hand, responds regardless of where what the phase of the grading is. So that's an example here. This neuron responds as long as the orientation and spatial frequency match up. Okay, Hubel and Wiesel described this back in 1962 and very elegantly pointed out. I don't expect you to read this. These are two passages that I really like from their 1962 paper. But they very elegantly pointed out that the complex cell is less specific in its response than its inputs. So it's essentially more invariant and less specific than its input. And generalizing from that, they basically hypothesized that maybe such invariance gets built up as you go through the successive stages of processing along the ventral pathway, and in the ultimate highest stages, you have these neurons that are highly invariant, and that's the basis of the behavior. Okay, so this is a invariance built on the basis of an encoding strategy where single neurons themselves build out their invariance, and that supports invariant recognition. On the other side, it is possible that neurons never build up their invariance to that level, as you see in behavior. Neurons tend to be very specific, but you end up getting invariances in perception, in behavior, in recognition behavior, simply at the network level because of a decoding strategy. Okay, and the truth might lie somewhere in between. All right. And so it's of great interest then to sort of look at what's going on in the intermediate stages. What kinds of invariances might you see in the intermediate stages with respect to position, size, rotation, conclusions, etc. And in my lab, we're focused on area V4, which is this stage over here, and we've looked at a variety of invariances, basically with respect to position, size, rotation. I got sucked up by that. And the interior fill of the stimulus, whether there is texture on the surface of the shapes, whether there are fills and outlines. I think Vivek was talking a little bit about this, and I'll talk about this later, and also, okay? So I'm hoping to get to all of these here. Occlusion is a major topic that we're thinking about working on in the lab, but I won't be able to get to any of that today. So if you're interested in that, please stop me and ask me later. Okay. We're looking at representational invariance for two reasons. One is to try and understand how this is achieved behaviorally, but we're also looking at invariances and representation is a great tool for us to think about how representations are built up in visual cortex. So it provides great predictions, and we can use the presence or absence of invariances to validate models, to improve our models, etc. And as you will see as we go along this talk. So now, it might seem like studying invariance should be an easy problem, right? If you want to look at whether a neuron is position invariant, you take a few stimuli, throw them up in front of the monkey, looking at a computer monitor, look at the responses at different positions, and ask whether they're same or different, and there you have the answer. But it turns out it's not so easy because these neurons have very complex receptor fields, and you really need to work out the prediction before you can decide whether the neuron is invariant or not. So I'm going to work this through for you with a very simple example. Okay, so let's say you're investigating position invariance of a P4 neuron. And you decide, okay, I'm going to take those three stimuli, and you're going to present it. Let's say this is the receptor field of the cell. You present the stimuli off to the left in the central position and off to the right. And these are the responses you get, okay? A second stimulus here, again, you do the same thing. These are the responses you get. And a third set of stimuli, these are the responses you get. Now, you might look at this and say, this is a neuron that likes this stimulus here in the left position, this stimulus here in the central position, and this stimulus here in the right position. So this is a neuron that responds in a position-dependent manner. Its stimulus preference is position-dependent. But if you were to, an equally good explanation for this response pattern is that this neuron simply likes the color red, right? Whenever there is red in the receptor field of the neuron, this neuron responds. So we can't just conclude that this is a position-dependent neuron just on the basis of an experiment like this. So it's really important for us to have an underlying encoding model, come up with predictions, and see if our expectation matches that prediction. Okay, so that's what we try to do in my lab. And the starting point for all of so feel free to stop me and ask me any questions if you have any as we go on.
Is it being sensitive to red a form of position independence?
I'm sorry?
Is it being sensitive just to whether it's red or not, regardless of where it is in the image, a form of position independence? Or,
yes,
yeah.
yes. So if you were to realize that the neuron really just cares about red, you might conclude that the neuron is position independent.
Yeah.
Whereas if you didn't realize that it cared about red, you might say the tuning is position dependent. You might say, oh, this is a neuron that likes this stimulus in one position and this in another and this in another.
Okay.
What's your definition of red?
We can talk about that later. So that's a good
I'm quite
question.
interested, yeah.
Yes, that's a good question. And this is something that's just up there for illustration
Yeah,
purposes.
I don't want to interrupt with that
Yes,
discussion.
yes. I'm happy to talk about that later. Okay, all right, so the starting point for all of the stuff that I'll tell you about today is a demonstration many, many years ago when I was a grad student in Ed Connor's lab, who's sitting front and center here, that neurons in area V4 are tuned for stimulation. What I mean by this is many neurons in area V4 are selective to convexities and concavities along the boundary of the shape. So let's say you have a receptive field of a V4 neuron, and this is a neuron, let's say, that's sensitive to sharp convexities pointing to the upper right, then such a neuron would respond strongly to stimuli that have that feature. It won't respond well to stimuli such as this one, which does not have a sharp convexity pointing to the upper right. It won't respond very well to this stimulus either, because even though the shape has a sharp convexity, it's pointing off to the right as opposed to the upper right. Okay, and we demonstrated that you can describe such selectivity in terms of object-centered tuning for boundary curvature. And so basically, we describe the responses of these neurons in terms of a two-dimensional Gaussian function, where one dimension was the position, angular position of the feature relative to center, where 0 was off to the right, 45 degrees was up to the upper right, and also the curvature of the boundary. Okay, curvature here defined as rate of change of tangent angle per unit contour length, and that will become important a little bit later. So basically, the responses of the neuron are dictated just by this feature and not by anything at anywhere else along the boundary. And so, based on this model, then your prediction would be that, these are all the shapes that the neuron would respond well to. These are all shapes that the neuron doesn't respond well to. Okay, so just starting from this encoding model, then you can make a lot of predictions about what kinds of invariances might you see in the responses of the neuron. For example, let's take rotation invariance first. Okay, we would not expect this neuron to be rotationally invariant because we're saying that this neuron is sensitive to a feature at its specific position relative to object center. Okay, so responds well to a stimulus like this, but not to a stimulus like this, which is just a 180-degree rotated version. And that's exactly what we see. So here's an example of a neuron. The x-axis here is just stimulus rotation. Y-axis are the responses of the neuron. The different shapes that we're using are in different rate scales here. So this neuron is selective for shape, so it responds best to this sharp convexity pointing to the upper right, pointing to the top, and not so much to this somewhat medium convexity down here. But the neuron is also very sensitive to rotation of the stimulus, responding best to stimuli pointing off to the right. I'm sorry, I told you that it was pointing up, but in fact, the responses are strongest to stimuli pointing. The stimulus rotation here is off to 270 degrees off to the right over here. Okay. So this might seem to be at odds with perception, where our experience is that we're able to readily recognize patterns and shapes regardless of the orientation of the stimulus. But as we talked about earlier with the Margaret Thatcher images, there is more to perception and more to rotational invariance in perception. Okay, so what we have here is this sort of specific tuning allows you to not only allows you to perceive the shape and its rotation. This rotation-specific representation. Okay, so the second prediction that the model makes is relates to size invariance. Okay, and as I said, the definition of boundary curvature that we use is not compatible with size invariant. So basically, the definition we used is rate of change of tangent angle per unit of contour length. And by this definition, curvature decreases as the size of the stimulus increases. Okay? So if a neuron is really encoding information according to this definition of curvature, we would actually expect the neuron to not be size invariant, so to be size dependent. But we can very easily convert this to a size invariant representation, as was also pointed by Peter Oliver earlier, and basically that you can either normalize the definition by length, or you could, next slide. You can either normalize by length, or you could measure curvature in a polar coordinate frame. So rate of change of tangent angle per angular length. So in this version, in this definition of curvature, you have size invariance, a size invariant representation. So you have the same curvature measurement regardless of the size. Okay. So we wanted to ask which would be a better model for the responses of the neuron by asking whether people neurons are actually size invariant. This helps us to sort of test the model and improve the model if we need to. Okay. So Yasmin El-Shamaili, who was a postdoc in my lab, designed a set of stimuli, basically a set of shapes ranging from extremely convex shapes with extremely convex features to circles, and then stimuli with concavities in them. And then we presented the stimuli in different sizes. And I'm going to call the polar version of the curvature definition as normalized curvature because it's normalized to the length of the boundary, and the rate of change of tangent angle per unit contour length definition as the absolute curvature. Okay? So the normalized curvature does not change depending upon the size of the stimulus, whereas the absolute curvature actually increases with size. And so this sharp convexity here has a lower curvature than this sharp convexity and this sharp convexity. So these stimuli here along the diagonal here are matched in curvature of the feature at the apex. Okay, so if you were a neuron that responded according to the normalized curvature model, then, and if this was a preferred stimulus, that reference should remain the same regardless of size. If you were a neuron that liked the encoded stimuli on the basis of this absolute curvature model, then we should be able to see a peak shift. And based on the size of these stimuli, we can actually predict precisely what size of a peak shift might you expect. Okay, so here are some of the predictions again outlined. So if you're a neuron that responded preferentially to convexities, then you should see a peak shift to the left. If it's a neuron that responded preferentially to concavities, you should see a peak shift to the right. Okay, and we'll look at a few example neurons here. This one is an example neuron that is tuned to absolute curvature. So the x-axis here are the stimuli ranging from sharpest convexity to circular to concavity, and the line colors here represent stimulus size. So black is the smallest size, and the cyan here is the largest size of the stimulus. And straight away you can see that there is a change in response magnitude with size, and that we see with a lot of neurons. Basically, many neurons will increase their entire response strength as we increase the size. For some neurons, 25% of the neurons actually decrease their responses with increasing size. And that's not the modulation we're talking about, and that we see in a lot of the neurons. What we're talking about is the shift in the peak. And you can see this here as you go from the smallest size to the largest size, there is a shift in the peak to the left. And you can capture this peak shift by computing the center of mass of these tuning curves, and that's what I've plotted here. You can see that there is a gradual but significant shift in peak, and this is predicted well by the absolute curvature model. Okay. But that was only 15% of V4 neurons show this kind of shift in peak. Most of the neurons look like this, right? Where you see no shift, you see a modulation depending upon the size of the stimulus. Again, this is a neuron that responds stronger to larger stimuli than to smaller stimuli, but there is no shift in the tuning peak. And so basically, we think that for all of these neurons, representation in terms of normalized curvature is the right way to think about it. Okay, and it was very exciting when we first saw this results, this was at VSS, and there was a neighboring poster from James Elder's lab showing that to measure perception in psychophysical subjects and ask them to report the curvature of objects, and you move the stimulus and also scale up the size, the results are consistent with the subjects actually computing it in an object-centered reference frame, consistent with a scale invariant report of curvature. So that seems well correlated with our results.
So you're saying 25% of the neurons respond to absolute curvature?
Yes.
Is there any other difference between those neurons and the?
Yeah, we have not been able to find any latency difference. We don't have any information about layer depth. That would be interesting. We're going to go back and do these experiments with, linear arrays, and so we'll see if we see any difference like that, but nothing in terms of latencies. For instance, I was, or in terms of when shape selectivity comes up.
So you're just segregating by the response rather than
Just based on which model fits better.
Does there seem to be any gradient between flat and whatever your maximal effect of the
Right, yeah, it is,
size
I mean,
is,
I can show you, this is all published, so I can show you the figures. It is a continuum, it is, it's just like simple and complex cells. It is a continuum. It's not two peaks. Here are all the neurons that are absolute curvature. Here are all the neurons that are, a normalized curvature. It's just there are neurons all along, and the extremes are what are well fit by each of these.
Does that fit with the notion that they're using one or the other definition of curvature?
But there are a lot of neurons in between that you can't differentiate between these two models. So they're equally good. Both models are equally good or equally bad at fitting these neurons. Clearly there are extremes, but there are lots of neurons in the middle. Okay, so the third prediction relates to position invariance. Okay, so I also told you that we think of this representation in an object-centered reference frame, which means that regardless of where you present the stimulus within the receptive field, your feature position is the same relative to object center. And so this means that your preferred stimuli and your non-preferred stimuli should be the same regardless of where you are in your scope field. Okay, your response magnitude itself might change, but your preference, your tuning preference is the same.
Is there any, how do you define the center of these different objects? So,
Yeah, so that's a good question. We've used center of mass, but we, I think we haven't done any experiments to differentiate between other. So you could consider a geometric mean
Mhm.
right? We've used center of mass, but we haven't distorted these stimuli and tried to ask what would be a good way, a good center position that these neurons are estimating.
Right. Okay. Cool. Thanks.
Okay, so what this model then predicts is that these should be the preferred and these should be the non-preferred, regardless of where you present the stimulus within the center field. And that's essentially what we find. So here are responses from one neuron. Each panel here is a different position within the receptor field of the cell. X-axis here are the different shapes. Y-axis is the rotation. So if you just take this center position panel, right? This is a neuron that responds strongly to these shapes. So these ones over here, not so much to the more, to the medium convexity shapes with a medium convexity, and it also likes this particular orientation of the stimulus. Okay, but this pattern is very, very similar across all of these panels. Okay, the response magnitude itself, given by this grayscale, changes between positions, but the pattern is very, very similar across all of these. And so we can assess position invariance by looking at the correlation in response between these two positions, for example. And the correlation is very, very high. It's the median of the distribution is about 0.85. Okay? So most of the neurons are very, very strongly position invariant. So what we think is going on is you can describe the responses by model like so. So let's say this is your tuning function for shape stimulus at the center of the receptor field. Then at the other positions, all you have to do is scale the response by some factor. So the position itself modulates the responses. That's a gain scaling, but the tuning peak does not change depending upon where the stimulus is within the receptor field. All right. The next thing to consider is about.
Sorry, can I ask a question in that context? In the receptor field, are you changing the amplitude and the variance, or?
We're not, in this case, we're not changing the variance at all, and we find that just an amplitude modulation
Is
solution.
enough?
Yeah.
Is the center of the receptive field always the highest gain, or is it just pure curiosity?
It's it's a definition thing, because when we map the receptive field, we
Right.
pick the position,
I see.
the maximal response as the center of the receptive field. So if we map the receptive field the way we think we should be, then it should match up. Okay. Okay, so the next, one last point would be to think about surface texture. So with all of these shapes, what we've done is presented stimuli with a uniform luminance gradient. We have not, or a color gradient relative to the background. So what happens when you paint a texture on the surface of the shape? And this is work that Tae-Chun Kim, postdoc in the lab, has done, and this is a whole study. And if you're interested in that, I can walk you through how we did it. But in the interest of time, and speaking of time, am I out of time already? Or okay, I'm going. Okay. So these are standard shapes that we've always used in the lab. We came up with a set of textures, and we painted these textures on the surfaces of these shapes. So, for example, these are the three shapes that we studied the responses of for one neuron, and then we presented the stimuli either as just a luminance gradient relative to, or luminance contrast. I'm sorry, I keep saying gradient. What I mean is a luminance contrast relative to the background or with a texture painted on. Okay? And what we wanted to ask was, is the shape tuning the same regardless of what the texture is that's painted on the stimulus? And this will become important to rule out other models for how such shape selectivity might arise. So these are the responses of one example neuron. So you can see that this neuron is selective for shape. It responds to this blue stimulus quite well, to the red at intermediate levels, and not so much to the green. And when you paint the different textures, which is along the x-axis, the blue shape continues to be the preferred shape. The red, the intermediate, green remains the bottom. Okay, And here's another example which, this is a neuron that does not respond so well to shapes, responds differentially to textures, but regardless of what the stimulus is, what the shape of the stimulus is, the texture preference remains very consistent. And here's one which is sensitive to both shape and texture, so responses are strong to this particular shape stimulus, this green stimulus, and when you paint the different textures, that the responses are highly modulated. Okay, so what we find is that these responses to this combination stimuli can be well explained by a product model. So you construct a tuning curve for shape and a tuning curve for texture, and a product of those explains the responses to these combination stimuli very well. Okay, and we also found that the timing of texture selectivity is on average about 30 milliseconds later than the onset of shape selectivity. So we think that there are two computations, one that imparts shape selectivity and another that imparts texture selectivity that come onto individual neurons. Now, why is this important? Well, there is an alternative model for how shape selectivity might arise. So with all of the traditional experiments we did, all of the stimuli with just a luminance contrast stimulus. And one idea is that selectivity to those stimuli could arise on the basis of tuning for higher order image statistics. So the basic idea is as follows. So if you take an image and pass it through a bank of linear filters, like the Gabor filters, oriented Gabor filters of different spatial frequency scale and orientation, then this is the output of those linear filters. Now you can compute higher order correlational statistics. So you could do linear across position, or linear across orientation, or linear across scale, and you can do the same with energy filters. And a weighted combination of these then could give you selectivity for complex textures. And that's how people have tried to explain texture selectivity in V2, where V2 neurons are sensitive to entire texture families, but not different members of a texture family, and also at the level of V4. But such a texture-based model cannot explain separable tuning for shape. Yes?
Sorry, what's a texture family?
Texture family, basically, each texture is defined by a set of higher order correlational statistics. Okay? And you can create images that are matched in this higher order texture statistics where the pixels are different.
Oh, I see.
Okay? So these are these two images, if you match them pixel by pixel, they're different. But if you compute these correlational statistics, they're identical.
I see, okay.
Okay? So at the level of V1, the neurons actually care about these individual members.
Right.
Okay? Whereas at the level of V2, the individual members don't drive differential responses. It's an entire family that drives similar responses.
Right. Okay, cool, thank you.
Okay? And sorry, I'm going through a lot of things fast, but yes, please feel free to stop me and ask me. So a similar model based on higher order image statistics cannot explain separable tuning for shape and texture, because the texture changes the higher order statistics. And so that should mess up your higher order, mess up your shape selectivity on the basis of texture statistics. Okay? So the experiments where we painted textures helps to rule out the possibility that shape selectivity is in fact based on selectivity for higher order correlational statistics. Okay. Okay, so far, I've talked about the curvature model, which is really a descriptive model. It doesn't, it's not a mechanistic model. It doesn't really tell you about how you might build up curvature selectivity. It's not image computable. You can't take some random image and pass it through the model because you have to do some pre-processing. So the question is, what kind of a mechanistic model can explain how curvature tuning that's invariant to pollution might be built up? Okay, one prominent image computable model for object recognition is the HMax model proposed by Poggio and colleagues. It's a hierarchical model of visual cortex. It's designed to achieve invariant recognition. And the first 4 stages of this model essentially have been shown to be able to fit tuning for boundary condition. Okay, so you can basically take these 4 stages and fit it to the responses of individual V4 neurons and get a good predictive power out of it. So let's take a look at just those 4 stages. So basically, the first level starts off with analogous to simple cells. So these are gabors of different faces and different orientations and spatial frequencies and scales. And in the next step, the first computation that happens is that there is max pooling across phase and position and scale. And essentially, you have this idealized complex cell, which is just sensitive to orientation. Okay, it's phase insensitive and it's slightly position insensitive, and it's straight up orientation selective. Okay, to build up selectivity for boundary curvature, like the kind we see in area B4, you might pool signals from multiple complex cells. And so, for example, if you wanted to build up selectivity to a sharp convexity polynomial, you might pull signals from the 45 and 135 degree orientation, and that would give you selectivity for that stimulus. And then, again, you can max pool across position, and you would get a position invariant feature selectivity for that. Okay? But what's basically happened is that you've the selectivity for a specific contour or a feature is now simply based on edge information. So all of the contrast information has been stripped away. All you have is edge information here. So one major prediction of this model is that responses would be similar to fill shapes and outlines, very similar to what Vivek was talking about earlier today. And so if you take an instantiation of HMax model, you see there is a good correlation in responses to filled shapes and outlines. The question is this what happens in visual cortex? Do neurons in visual cortex respond similarly to these stimuli? This prediction seems very consistent with perception. We're very good at recognizing objects regardless of whether they're outlines or not. Even young children are very good at this. We've exploited this since very early K-3. So it seems intuitive and it seems to make sense, but nobody had ever asked this question of whether neurons actually respond similarly to these 2 stimuli. And so Dina Popovkina, who was a grad student in my lab, created a set of stimuli that were matched in every way, except that one set of stimuli did not have any interior. Yeah. Yes, 5 minutes. Okay, thank you. Okay, so we looked at the responses. We compared the responses to these filled and outlines, and there are some neurons that respond in a very similar way. They're similarly selective, regardless of whether the stimuli are filled shapes or outlines. Okay, responses are stronger to filled and weaker to outlines, but there is a strong correlation. But other neurons respond like so. Again, this is also a shape-selective neuron, but responds only strongly to filled shapes. When you look at the responses to the outlines, it is not shape-selective. The dynamic range of the response is weak, and there is very clear correlation. This is another example neuron that responds with a nice dynamic range for outlines, not so much for filled stimuli. And a last group of neurons that responds to both sets of stimuli, but there really isn't any correlation to speak of. Okay. So the neurons that are behave as predicted by the HMax model and behave as we predict with behavior are only about 20% of neurons. Vast majority seem to really need contrast, local contrast in driving the responses of these neurons. There are some that like outlines only, but the majority of the cells seem to care about this. Okay, so we realized we had to go back and change the model, and I won't talk about how we managed to change the model in the interest of the time, but suffice it to say that we used two strategies, one in which we removed the max pooling across phase, and in another in which we added an unoriented filters which carry contrast information. So basically, we tried two different strategies for providing contrast information at the level of V4, and we were able to predict the responses of the neurons. And this result might seem like it's at odds with perception, right? But all of this stuff was done with single isolated objects. You're matching, you're asking whether subjects can recognize these objects just on the basis of outline, but they were isolated objects. If you were to recognize something in a natural scene just on the basis of edge information, it is a tremendously difficult problem, and I'll illustrate that with this. Okay, what I've done here is just taken a very simple image and passed it through a candy edge detector, and I'm giving you all of the edges here. Okay, I can bet you. Well, maybe somebody can try to guess what that is. Maybe somebody could. But I don't have much time, so I'm just going to show you the image. And when you provide the contrast information, it becomes so easy to recognize what that image is. So I think these V4 neurons are really optimized for scene parsing and scene understanding in natural environments. And this whole outline similarity in recognition of outlines is something that we can do apparently with just 20% of the neurons. It's a simple task that we can do. It seems as though maybe these neurons are not primarily trying to do object recognition, but maybe something more complex, which I believe is scene parsing. Okay. Okay. So in the last 3 minutes I have, I'm going to. So we still don't have a very good mechanistic model for how these selectivities might be built, especially in the context of invariances, in the context of curvature tuning that's translation invariant. So lately we've been looking at deep neural networks to see if there are units there that are similar to V4 neurons in terms of their tuning properties, and whether we could gain some insight about how to build up these circuits on the basis of the architecture that we see in these networks. Our interest is not in asking whether the nets are like the brain, but in actually identifying individual units that might have properties similar to V4 neurons. So we've mainly been focused on AlexNet, which won the ImageNet contest in 2012. And when I say we, this work is mainly done by Dean Hospital, who's a grad student in Bear's lab. And I won't go through the details of training or validation of this model because we got a tutorial earlier today on deep nets, and I'll go straight to the results. So the first layer of the convolutional net, people have shown that neurons have the features are very similar to V1 receptor field properties. So you see orientation tuning, spatial frequency, selectivity for color. So the question is what happens deeper in? So we probe these networks the way neurophysiologists would, and we playfully call it artiphysiology. And we basically use the same set of stimuli that we use to study V4 neurons, and we fit the same models, and we ask, are these neurons, do they have the same invariances or dependencies that V4 neurons do? Do they show curvature sensitivity? And it turns out a lot of neurons in the network show curvature tuning. So this axis here is a goodness of fit measure, V4 neurons. This is the cumulative distribution of V4 neurons in red. And except for con1, right, all of the convolutional layers and the fully connected layers show a lot of neurons that are curvature tuned. Okay, at least they appear to be curvature tuned. But the minute you add the constraint of translation invariance, a lot of these units drop out. So I'm going fast through all of this because Vivek is standing over there. So when you add translation invariance, V4 neurons appear to be the cumulative distribution for V4 neurons are right here. Now, Con2, Con3, Con4 all have much worse translation invariance as compared to a V4 neuron. V4 looks quite like units in Con5. Okay, so we can actually find specific examples in convolutional layer 5 that have tuning for boundary curvature selectivity. That's position invariant, the way V4 neurons are. Okay. Another constraint we put in was the fill outline. This is training, I won't go there. Fill outline invariance. Do units in deep nets have the same fill outline invariance? V4 neurons overwhelmingly don't. And the question is, what about units in deep nets? It turns out that most of the units look like this one here, where the responses to fills and outline stimuli are highly, highly correlated. So deep nets seem to be, have this fill, they deviate from V4 neurons in terms of their fill outline invariance. Okay, so this is the distribution of fill outline invariance across various layers. They're all stuck. The median is 0.9 or about for all of these layers, and V4 neurons look like this. Okay, but we can still go in and look at individual units there and ask, there are some units that don't have fill outline invariance, and we can ask, okay, what is the architecture of these units compared to units that show fill outline invariance, and then try to understand from that how people go up. And I'm going to read all that, and thank you for your attention and taking questions.
So a couple of questions.
I just wonder whether you have looked across the fence into the motor control literature, because there the attempt was to show tuning to direction, tuning to velocity, tuning to curvature in movements in cells of the motor cortex. It's different, but nevertheless, I just wonder whether, there's at some level of abstraction you can see similarities.
Yeah, that's an interesting question. That's something that I haven't really looked at that in the literature. So are there models for movement dynamics?
There's a whole industry now. It started out with showing the directional sensitivity of populations in the motor cortex to reaching directions.
Yes.
And then subsequently, there was shown sensitivity to torques in joint space, and also somewhat related to curvature changes and velocity relations.
Very interesting. Yeah, I'll have to look at that.
I can.
One more question.
From the tutorial, the deep nets had the non-linearities. In that case, what's the meaning of a receptive field? If you cannot actually measure it?
Yeah, so the meaning of a receptive field, that's
Linear property.
yeah, so basically the way we measure the receptive field of a unit in a deep net is by presenting the same stimulus and moving it along and asking how the response drops off. So for example, the green line here basically shows you the response magnitude of a single unit. And so as I, so it might be easier with my deep net slide. So each one of these units has like a certain capture range. So it's 11 pixels at FC1, con1, 51 pixels at con2, etc. So they have a certain capture range where they get the inputs. And so that essentially defines the receptor. But you can also measure it by moving the stimulus across and fitting it to the function.
Right, thank you so much.
Yeah, thank you.
All right. right, our next speaker will be Jacob Feldman, who will provide a Bayesian perspective on